In this video, I want to talk about some performance metrics of DACs. The basic idea of behind talking about and discussing performance metrics is that it gives us an idea of the kind of errors, the kind of non-idealities that creep into the performance of the DACs. So DACs basically take a digital code, multiply it with a constant, and give an analog output that is equal to the constant times the digital code. But there are lots of errors that can go in this process, and that's what we are looking at by using performance metrics. Performance metrics are also metrics that are used to see how well a DAC behaves. And when you're choosing a DAC, especially for a critical application, you may have to look at many of these characteristics in quite some detail and think about how it affects your application. So let's take a look at few of these performance metrics. The first metric I want to talk about is differential non-linearity. But before we talk about the metric itself, let me just kind of help you see what this graph is. On the x-axis, we have the digital input. On the y-axis, we have the analog output, right? And this dashed line is the ideal curve that we would have between the digital input and the analog output. Okay, another way, I think it's ideal in a certain sense. So it's ideal in the sense that what we are doing is we are drawing a straight line between the lowest value of the digital input and the analog output and the highest value, and we join them with a straight line. That's what this line is. Okay, so let's having said that, let's look at differential nonlinearity. So differential nonlinearity is the maximum error that you can get uh, at the output for a particular bit. So you can see if this curve was ideal, what we would have expected is that all the step sizes would have been equal. But because of certain nonlinearities, we can see that there is a bigger step size here than, let's say, at this transition. Okay, so the maximum of this is referred to as the differential nonlinearity. What we are seeing here is, so it's not, the differential nonlinearity is this step size minus or take away 1 LSB, the step size that it should have been. So it's the increase in step size, which is the differential nonlinearity. Another metric that we often use is called the integral nonlinearity, and it tells you the maximum deviation from this line which in the real curve. Okay, so if this system was completely linear, what you would have seen is that this curve would have just been around this line, right? But because it's nonlinear, there's a deviation. So the curve actually goes something like this. It's a curved line here. So the maximum deviation, this deviation, is called integral nonlinearity. The offset is basically the analog output when the digital input is 0. You expect the analog output to be 0, but usually in DACs or in some DACs you can have offsets. So that's the offset. Gain error is the deviation of this line that we have from an ideal characteristic. The ideal characteristic would have a slope of 1, and this might have a different slope, and the difference there gives you the gain error. Okay, so those were static characteristics. Now let's look at some dynamic characteristics. Let me explain this graph a little bit here. So as you know, all digital systems work based on a clock, right? So you have a clock input here, okay? And at every high of the clock, there is a what should I say? There is an analog value produced. The digital to analog converter works and it produces a output. Now when the clock is applied, the digital input is applied, and the digital input is applied, and analog output comes in, is developed over time. So it does not happen that as soon as you give the digital input, the analog output suddenly appears. It takes a bit of time for the DAC to actually do the conversion. So the time that it takes for the analog output to settle down to its final analog value is called the settling time. Sometimes when you have an analog output, you have these glitches in the DAC output, and the glitch impulse area tells you how big that glitch is. Okay. Latency is the time from when the clock is applied to when the analog output becomes stable. So it is basically the settling time plus the time that it takes for the digital input to actually be applied to the DAC. So that's the latency. How long does it take for the analog output to become stable after we ask the digital to analog converter to do the conversion? You have a signal to noise ratio and signal to noise plus distortion ratio in DACs as well. And basically, they measure what is the relative power of the signal with respect to noise and with respect to noise plus distortion. And usually, these are measured when the input is a sine wave, and then you measure how the output comes. uh, you have noise. Noise is basically random noise, and distortion is basically harmonics of the sine wave that you're applying to the input. The basic idea is that a sine wave is not exactly a sine wave. It has got some non-idealities, so it will have higher frequencies associated with it, and those may pass through uh, to the output. Or the device may be non-linear, which results in some higher signals coming, some higher frequencies coming into your input. So distortion is basically because of the harmonics of the sine wave that you're applying.